Good afternoon, everyone. Let me just wait a few seconds here so people can join the lecture. Okay, share. Are you able to see the slides, please? Anyone? Perfect. Okay, so let's start our today's lecture. We last couple of lectures we talk about how we do the analysis for fluid flow in systems, and we mentioned that chapter 3, 4, and 5 are basically dealing with different type of analysis for fluid flow. And as I mentioned again, that was just an introduction to the fluid flow. So it's kind of like, there is a lots of maybe detailed information that we don't have the time, and it's not actually part of the objective of this course. So basically, we are focusing on the most important fundamentals that all engineers need to know about fluid flow and in the fluid mechanics subjects. So today we're going to talk about different type of analysis. So chapter 4 is basically talking about the differential relation for fluid flow. So instead of like looking into the control volume, as you remember what we did for the conservation of mass and the conservation of momentum and energy in chapter 3, what we're going to do today is make an introduction to why like engineers and scientists were looking for what we call it the differential analysis form for fluid flow. So we're going to apply those ones on maybe the conservation of mass, because conservation of momentum and energy would be much more involved in type of analysis. And as I mentioned, the scope of the course, we're not going to go into these type of details. But differential analysis is basically, it is the only difference is, considering control volume, you take the whole component and you just say what is coming in, what is going out. The differential analysis form is basically looking into dividing this whole domain where the fluid is flowing into small little volume. And this small little volume could be in the order of, a micron if you are interested in small little detail. Sometimes it's a little bit more, but, we call it like the grid. So we call it what we, an infinitesimal small control volume. So infinitesimal mean here as very little small control volume. And why we are doing this in this type of analysis or the differential form is to get more detailed information about fluid velocity at every single point in the flow field. Okay. For example, sometime we need to design the hydrodynamic shape, or the aerodynamic shape of a car, or the hydrodynamic shape of a turbine, water turbine, or even looking into erosion in river and dams, right? So now we are interested not on overall bulk analysis. We are not interested in total effect on the overall system, but we are looking into small little details. Some other application related to deposition in blood flow and blood streams, looking into, for example, in automation system for, let's say, a computational system, you need to decide about air distribution, around these servers. And you are looking into developing some understanding of what will be the heat transfer from those equipment to the fluid. So, those type of analysis need much more kind of detailed information. And we do all this with using a computational fluid dynamics. And computational fluid dynamics is a topic by itself, but computational fluid dynamics is basically converting the mechanical momentum and energy equation into digits and some numbers on the computer, so you can calculate those numbers. And by doing this, we have to divide the whole domain of the fluid into very small little control volumes, and those small control volume is almost approaching zero, the size of these approaching zero. But of course, like, different application will require different size of these analysis. So you can imagine if we are looking into bloodstream, we are looking into maybe the grid size or the small volume in the order of like, maybe 0.001 millimeter. But when we are talking about fluid in rivers, maybe those control volume could be in the order of like, 1 meter each, kind of size of these control volume to do this analysis. Okay. So that's the purpose of making this introduction in this chapter. But before we do this, before we even understand how this is kind of analysis is transforming the equation, right, the conservation equation into the computer code and doing this, we have to understand few principles, and those principles are related to kinematics of the fluid. Okay, velocity, acceleration. Okay, how we visualize the flow, how we look at those flows, and and come up with some kind of general understanding of the behavior of the fluid. Okay, and that's why in this chapter we're going to focus more on these understandings, and then we apply some of this understanding to the conservation of mass equation. Okay, so we're going to introduce some concept and definition on what we call the streamline, steady flow, unsteady flow, what is the acceleration, what is the velocity, and so on. Okay, so fluid kinematics, if you remember in the beginning of this course, I mentioned different subjects in the fluid mechanics, and one of these branches of fluid mechanics is kinematics. And the kinematics here is dealing with the motion itself without considering the forces. So the motion mean what is the position or what is the location of every single element of the fluid as it goes, or what is the velocity of this element, or what is the acceleration of this element, and so on. Okay, so in order to do this, we are basically understanding these kinematics first, and then we apply the forces in order to get the whole picture of of the fluid dynamics perspective. Two ways of expressing this fluid motion. Okay, there's two way, engineering and engineer and scientists actually used in the the analysis of the small or the detailed analysis of the fluid flow. One is called Lagrangian approach, and one is Eulerian approach. Okay, the Lagrangian approach is basically looking at every single particle and tracking these particles. So just go with the particle and look at what is the velocity of this particle, what is the direction of this velocity, what is the acceleration, position, and so on. Right? Some of these analysis is required. For example, let me give you an example. Like rocket engines. So in many rocket engine, in order to increase the thrust, they added certain kind of droplets into the air or the combustion gases in order to increase the mass. But those particles can generate some erosion in the in these thrust nozzles and stuff like that. So they need to get a more understanding of where is those particles are and how it hits the surface of this nozzle and so on. So in this case, Lagrangian approach is very appropriate to this. But of course, the details of analysis and the depths of analysis will be require lots of extensive kind of computational simulation. While the other approach, we call it the Eulerian approach. Let's do this first. Like Eulerian approach is control volume approach, but not the whole control volume of the system. It's just dividing the domain, dividing the whole flow field into a small little volume, and then apply the conservation of mass, momentum, and energy for each control volume. So imagine you have a domain, like let's say, for example, just give you an idea. You have a domain like this. And flow is coming in, flow is going out. And let's say, for example, you take this whole control volume and you divide it into grids. Okay. I'm just, quickly doing this very, right? And each control volume, each one of these volume, you solve the momentum, mass and energy equation. So you locally, right? Of course, if you reduce the size of this, that means it's almost you are approaching a point, okay? But imagine now if you have 100,000, control volume in this domain, that means you're gonna solve the mass, momentum, and energy equation for these 100,000 points. And then your computer simulation is basically try to find the final result at every single point or at every single control volume. Okay, so now you have more details about the fluid velocities, the fluid, right? And then you can plot these nice colored graph in the computational fluid dynamics or the streamlines to see exactly what's happening inside the fluid. So imagine if this fluid is carrying some solid particles or or it has maybe diffusion of heat transfer or something like that, you might see much more detailed information in these ones. Okay, so Lagrangian and Eulerian approach are the two type of analysis. So I'm sure you guys are expert in this, but remember the position vector. Position vector is when you have a point and you are referring to the position of this point from a certain coordinate, right? So if you are looking at the Cartesian coordinate system and I have a point like this, so I can say, for example, this is my, so this may be the X component of these points. This is the Z component of this point. This is the Y component of this point. So I can actually put the vector of the position. We call it for example, R, and R of T mean, so at time T, right? Because this particle can be moving with time, which means that I will have to find out, for example, in this case, the position as the time is passing. Okay. So Xi and Yj and Zk those are the vectors, or those are the position vector of these components. So in this case, we are identifying the location of these points. Of course, if I need to find the velocity, for example, in this case, what I need to do for this case, the velocity will be basically the derivative of this position vector with respect to the time. Okay, so if I'm going with this particle, as I mentioned, using the Lagrangian approach, or tracking this particle position, if I need to find out the position of X of these points, the component X of the position at a certain time, that means I am kind of differentiating with respect to the time. So the position vector will be dx by dt, dy by dt, dz by dt, and of course the component ijk. So instead of a position vector, I can convert the position vector by differentiating with respect to the time, and now I have what we call it the velocity vector. Okay, and the velocity vector will be the same thing. You have a component of the velocity in the x direction, the component of the velocity in the y direction, and the component of the velocity in the z direction. So in the 3 dimension. Or if I'm using r, theta, and z, the cylindrical coordinates, so I can define the velocity of any single point by 3 component, x, y, z, or r, theta, and z. Okay, so same as for solid mechanics is the same as for fluid mechanics, but now we're talking about a particle of the fluids. Okay, so in this case, we can find out the velocity, and if I need to find out acceleration, I can do another differentiation in order to find acceleration. Okay, control volume approach or Eulerian approach. So this Eulerian approach is looking at one window here. So this is one window here, and this window is as if you are observer of a window or a control volume, and you see what's coming out and what is coming in, right? So these kind of methods are more appropriate to a lots of fluid mechanics problem, okay? And in this case, we are putting the velocity as a function of x, y, z, and t, okay, which means that at any single point of the fluid, the velocity can be changing in the x direction, can be changing in the y direction, can be changing in the z direction, can be changing locally at the point with time, right? So I can put the general expression for the velocity to be, in the vector form like this, okay? Of course, these are the components, or maybe like, if I'm looking at a path function, like, along the path, like, if taking this in the mass and in the solid mechanics as well, you can either look at, a polar coordinates along the path, or, with a Cartesian coordinate x, y, and z, okay? So those are like, simple fundamentals. So now, if I need, as I mentioned, if I need to find even acceleration, I can take the, see, this is a position vector, which is u, v, and w, right? And now the acceleration vector will be even another derivative of the same vector. And now I can get du by dt and dv by dt and dw by dt, which is our acceleration component, right? Okay. So luckily, we are not going to get into much more detailed about, this Lagrangian formulation, because it's much more kind of extensive subject. But, I have to tell you, like, in fluid mechanics, in general, we use what we call it the Eulerian approach, or the control volume approach, for much more simpler problem. And this control volume approach, or Eulerian approach, is very simply is looking at the acceleration as, a function of the velocity is a function of x, y, z, and t, and each component will be function of x, y, and z, and t. Okay. Any questions so far? I'm just putting some kind of fundamental background before I get to what we need to discuss today. Any questions so far? Hey guys, nothing? It's okay. Everything is okay. Are you sleeping or what? Anyone? Do I have people in this room? Like, I'm talking to myself, or some people around? Okay, cool. So vector components can be represented in 3 components, and each component of this velocity can be a function of x, y, z, and t. Okay. In order to understand this, I hope you understand it, but let me explain it even more. Okay. So if I look at one component, let's say I have a planar, because it's easier to was x, y, 2-dimensional type of problem. I have x and y, let's say, for example, and this particle here has this velocity. And let me say that this dimension here, or this length of this velocity here, okay, is an actual to scale vector. Okay. Now, if I need to find out the component of this velocity, I have 2 lines. One will be v and one will be u. And this is basically your component in the x direction, and this component in the y direction. How u, okay, and maybe this is a question, so just to make you a little bit awake, how u is function of x, y, z, and t. Let's say, for example, here we have 2-dimensional fluid. So how u is function of x and y, and also the time. Can anyone give me an idea? So this is a particle at the position 1. How u is a function of x, y, and time. Can u be function of y or no? That's correct, Trevor, right? Because if, for example, now if this particle of the fluid now is here, okay, so this particle moved and now it's here, okay, and now the velocity is, for some reason, is this value. So this is a velocity now, okay. So now if I need to find out the components, those are the components. So this is u2 and this is v2, okay. Now from 1 to 2, I change in the x and also in the y, which means that u change because I moved distance x and distance y. So the component also will be function of x and y. Okay, so how about if this u at a certain time 0, maybe at a time, t equal 2 seconds, 3 seconds, maybe this component become like this. Maybe the velocity is becoming like this, right? So even though you are at the same location of x and y, but now v, okay, could be with time. Okay, which means that in this case, if I have u could be function of x, y, and t. If I'm talking about only a planar type of analysis. Of course, if it's also 3-dimensional, it's going to be function x, y, z, and t. Okay. So total derivative, I hope you recall this when we are talking about total versus partial derivative. The total derivative is du by dt, or because we said acceleration is basically the second derivative of the velocity. The second derivative of the position, which is the first derivative of the velocity, right? So acceleration. This should be x, right? So acceleration in the x direction will be du by dt, okay? But because u is function of x, y, z, and t, right? The total derivative will be, remember how we do this, analysis? When we have a function that is variable of a multiple variable. So what we do is basically like here, what we do in order for to get the acceleration, we get du by dx, right? This is what we call it the derivative. So du will be du by dx plus du by dy plus du by dz plus du by dt, right? This is a total operator, right? The total derivative operator, okay? When I get du by dt, which is by dt, okay? So basically, I am kind of, dividing this whole equation by dt, right? Or applying the operator in the denominator, right? So d is going to be du by dx by dt, du by dy by dt, du by dz by dt, du by dt by dt, which is, this will be gone. So now you have dx by dt is your u, dy by dt is the vector v, dz by dt is the vector w, which means that the acceleration component in the x direction will be presented by, 4 component. Why is that? Because the function itself is dependent on x, y, z, and t. So the total derivative or the total acceleration will be, 4 components. Okay, 3 components are in relative to the position, or the change with the position, and the 4th one will be the the change with time. We call the first 3 component here. Of course, we can do the same thing for y. We can do the same thing for z. The only change here is this is your u all the time. This is your v. This is your w, right? So those are the components in x, y, and z. Okay. The first 3 components here dependent on the distance, the location, the change because of the change of the location. The 4th one here is the change locally. So at the same point, but with time, right? That's why we call the first 3 component here is, or these ones here, your convective acceleration. And we look at this last one here is local acceleration. Okay, so in general, every component of the acceleration are two parts. One is convective. Convective mean convection is related to space, right? So the change with respect to the space or the distance or the domain, right? And then there is one change here related to the local variation at the same point, but now with time. Okay. Okay, so this is basically what we said. So d by dt is term is local, and the three components in addition to this will be our convective acceleration. Okay. Now let's get into the topic. Okay, the topic here is talking about fluid flow domain, and the fluid flow domain I mentioned to you, it is described in what we call it, like in the differential form. It could be by position, by velocity, or by acceleration. So those are the description of the flow, right? How can we describe the flow? How can we describe this type of flow? And why it is important to describe the flow? Okay, let me tell you that this description of the flow is very important for your understanding as an engineer when you solve a problem. Okay, when you solve the problem, you have to really, from the beginning, know what is this problem. What is this problem as a function of what, right? Defining your variables is very important. Okay, that's why you need to know, for example, if your problem is steady or unsteady, right? If your problem is uniform, and what kind of parameter is uniform and what kind of parameter that is non-uniform. Okay, is your problem is one-dimensional or two-dimensional? For example, when I plot these here, this is a two-dimensional problem. So I kind of assume that I'm solving something related to a two-dimensional problem versus three-dimensional problem or versus one-dimensional problem. Okay, those are the common stuff that we heard about before, maybe in many other topics, not only fluid mechanics. In addition, we have additional topic for the course here is something called rotational versus irrotational flow. What is definition of, or something called ideal or real flow. Ideal flow, what ideal mean flow? Okay, so the irrotational flow is the ideal, right? So we call this is ideal, another name for it. Okay, so ideal, what is ideal mean in the fluid mechanics in this case? What is compressible versus incompressible fluid mean? Okay, and then the last part here that we're gonna cover in chapter I think 6 will be laminar or turbulent type of flow. All these classifications are going to be important when we are dealing with analysis of fluid mechanics or analysis of fluid flow in a system. Okay. So first, if you remember steady mean, what is steady? If you remember, I explicitly said that in one of the lectures, I guess. We spent time talking about this. What is steady mean? Yeah, people are saying the same exact answers. Constant and hydrostatic. All I have seen this not changing. Oh, all the same questions. Looks like you didn't hear me talking about this before. Yes, like constant with time, no change with time. Okay, all the other words are not accurate. Okay, so which means that d by dt for a steady is 0. Of what? Of everything you're saying, right? Here, for example, we're talking about velocity. Yes, the change of the velocity with time is 0, right? But steady mean, whatever variables that you are talking about here, any, okay? So steady mean here, steady is like, change, the change with time is 0. Unsteady mean, the change is not 0. Very simple. Okay, so the definition now, okay. So remember this, okay, because you're going to solve a problem and then you have to tell me if this is steady or unsteady. Uniform or non-uniform mean, uniform mean everywhere. Uniform is with respect to position, which means that if I am an XY plane, I'm looking at every single point at every location. The stuff that is uniform mean it's the same, right? So which means that the change with position here. So this is like the position vector, okay? So d by ds is 0, d by, oops. So those x, y, and z, or s. S here is polar coordinates, see, right? So, or, right? Yes, I think, you know, when you are talking about ideal flow, because ideal flow, no viscosity, that means the velocity is not changing. That means it is a byproduct, right? So frictionless flow is a byproduct of this is a uniform, right? So of course, real fluids that has viscosity that is considered, or when you have friction, that means you will have non-uniform flow. Good question. Okay. One-dimensional, two-dimensional, and three-dimensional are related to x, y, z, or r, theta, and z. Okay, if you are talking about Cartesian or, you know, cylindrical, right? So if I have a you know, variation in x, y, and z, that means I have a three-dimensional type of flow. If I have the, you know, variation in x, y, that means it's only two-dimensional. That if I have the, you know, variation that only in x and z, that means it is two-dimensional. If I have variation in theta and r in a cylindrical coordinates, that means two-dimensional. If I have variation in at every r and every theta and every z, that means it's a three-dimensional. No, Marcus, like, you know, steady and unsteady. We're talking about general parameters here, right? Of course, if you are interested in the velocity, yes, you know, this will be valid, but it also can be valid on other things. Pressure, for example, if my problem is related to pressure variation or temperature variations or stuff like that. Okay, so this is general definition of, you know, flow field or temperature field or pressure field, or like, right? It just happened that we are concerning of velocity and acceleration in these parts of the lecture. Okay, so 1, 2, and 3 dimension. Ideal flow is related to no shear stresses, which mean, what do you mean ideal flow here? We talk about it like, you know, ideal flow, no shear stresses. What does it mean? Okay. Oh my God. Yeah, hydrostatic, incompressible. Has nothing to do with that. Okay. Newtonian, nothing to do with that. No. Ideal fluid mean? Newtonian mean what? What is Newtonian mean? What is Newtonian mean? Okay, I hope like you guys, you know, start kind of controlling your technical term to mean something that's specifically in your mind, right? So don't come up with definition that is not clear in your mind, okay? What does Newtonian mean? What does the Newtonian definition mean? Anyone? Shear stress is linear, right? But actually is linear with the strain, right? The shear stress is linear with the strain that is happening in the fluid, right? I agree with that. But in this case, we, as a result of this, we put the proportional term, we remove it, and we put the viscosity, which is constant. It is no static here, okay? We're talking about fluid flow, okay? No shear, oh, you mean like, you know, shear forces here mean this is static? No, it doesn't mean that. So what I mean here is, if there is no shear stresses here, Of course, in the static, yes, well, we say there is no, but no shear stresses mean here what? Yeah, no shear stresses in general mean what? Yes, it is. Yes, I know it's for the static. Yes, it is no shear stresses, but the opposite is not the right way, right? Because you have no shear stresses mean no viscosity. I like you, Spencer. Okay, no viscosity. Viscosity is zero, right? So ideal mean is never exists, right? Ideal is not something available. Static is something, yes. Can fluid be static in real life? Yes. Tank filled with liquid. This is real stuff, right? It just happened and it doesn't have any shear stresses. But ideal fluids, that fluid even moving, but I'm assuming this fluid is moving with an ideal condition. That means I'm assuming that the viscosity is zero. And this is assumption, huh? This is nothing, you know, not real, right? Ideal mean is not real, it's not, right? Why you are doing this definition, or why you are doing this, approximation, as I mentioned to you before? There's so many reasons for that. Some of very obvious reason is to simplify the problem and solve it, because sometimes you have a very complex problems, very, very complex problems, not the problem that we just solved in this exam, right? Or in this class, right? You might have a very complex, relation that has a viscosity. And if I put the viscosity zero, all this is zero. Now I'm focusing on something else, solve the problem, get on a very quick understanding, and then make the problem a little bit more complex, one step at a time. So sometimes the approximation is valid for a certain region. So viscosity is zero is for ideal flow, and ideal flow is referring to something called irrotational flow. And what is irrotational mean? Irrotational and rotational is looking at, I don't know if you can see this, this pen, for example. Okay, if both particles are moving with the same velocity, okay, do you see this? Can you see what I'm trying to explain or no? I know it's a small little window, okay, but if you have both point in this kind of pen is moving with the same velocity, which means no viscosity effect, you remember? Because if you have a viscosity, that means point here in the fluid and the point far from this point here will have a different velocity, right? Because of the shear stresses and so on, right? But now if I have no shear stresses, or a viscosity is equal to zero, those point has the same velocity. You see that the pen is translated, right? As the fluid is moving as a solid body, right? But now if you have one point is moving faster than the other one, so what's going to happen after some time? If one point is moving faster or relative to the other one by different velocity, what will happen? It will rotate, right? So which means that rotational is a real case of a fluid mechanics. The particle of the fluid is deforming while moving and so on. But irrotational is almost as you feel like, this kind of, element of the fluid, is moving as a solid body. There is no irrotation, which is basically, in this case, you have a viscosity is equal to zero, okay? Incompressible and, okay, let me ask you before I put this. Incompressible and incompressible. Compressible and incompressible related to what? Density, thank you, all right? Because density is a definition of compressible and incompressible. If the density is variable, you have incompressible fluids, okay? If the density, if the density is constant, right? And I mean here, like, with a certain value, because we all know that liquids, might change its density slightly if I heat it or something like that, right? I'm not talking about heat transfer here. I'm not talking about this type of condition. So I'm talking about, in general, liquids are considered to be incompressible, okay? But gases are considered in general to be compressible fluids, okay? So if the density is constant, that means this is wrong, right? It's the opposite. Okay, this is incompressible. okay, and this is okay. So incompressible mean density is constant. This is incompressible, and density that is, you know, not constant, that means it is compressible fluids. Okay. Now let's solve this problem together. Okay. Given an Eulerian velocity vector, v is given as 3t. Okay. I x z j t y square k. This is a velocity vector. So this is a vector that we have here. Describe the flow. First, what do you think about this, you know, vector here? Do you think this is steady or unsteady? Steady or unsteady? Unsteady. Why? We call it unsteady. Yeah. Why? Since it is changing. Yeah. Complete the sentence. Lian, complete the sentence. Changing with what? No. Changing with what? Was time. Right? It's only t. Why is it changing with time? Because it's a function of t. Right? Does it have to be like every component to be function of t? No. Just like once I found t in whatever part of the whole vector, that means it is changing with time. That means it is so unsteady. So unsteady because yeah, v is function of t. Okay, and v is like v mean whatever this vector, like any component of the vector is. Okay, okay. Compressible or incompressible? Compressible or incompressible? People want to use the time to understand. Assume. We are not going to assume anything. Can we judge these? Can we, you know, let me, okay. So we cannot really say anything about that. Okay. I like that more because there's nothing really talking about density here, right? So which means that we cannot judge if this is compressible or incompressible fluids. We don't know, right? Okay. 1, 2, 3 dimensional. Yeah, Marcus, we cannot tell this from the equation. We cannot do the density. Yes. 3 dimension. Why 3 dimension? X, Y, Z. I like that. Excellent, guys. Yeah, it's not U, V, and W, okay? It's not the component U, V, and W. It is X, Y. No. Carl, now you're going to change the whole thing, right? I was just about to say that. It's not because U, V, and W. Because U and V and W could be all function of X. And now it's only one dimensional problem. Okay? So it is related to X, Y, and Z. Okay? So this is 3 dimensional because V is function of X, Y, and Z. Does it have to be every component function of X, Y, and Z? No. Just like if I see X, Y, and Z in the overall vector, that means it is 3 dimensional. Okay. Can I say uniform or non-uniform here? Is it uniform or non-uniform? Non-uniform. Why? Because the velocity is changing. The velocity is not the same as everywhere, right? The velocity is changing, right? So this is, you know, V is it doesn't have to be X, Y, and Z. It could be just one of them. Okay. Okay. What can we find out acceleration? How can we find acceleration? How can we find acceleration? Acceleration X is U du by dx plus V du by dy plus W du by dz plus du by dt. Okay, and this is all just one vector. Okay, I can just find out this. Du by dx, u is not a function of x, which means that this is 0, right? Okay, now v is, what is v? Is xz, okay? And du by dy actually also, du by dy also 0, because du is not a function of y. U also is not a function of z, that means this is 0 too, right? So du by dt is 3, right? So ax here at the end, it is 3. Okay, ay, this vector, is u dv by dx plus v dv by dy plus w dv by dz plus dv by dt. Okay, dv by dx is, first is u, right? So 3t, right, times dv by dx is, I'm doing simple exercise, guys, here, right? Simple math exercise, right? Is it simple or no? It's a simple, but you have to be careful about, like, when you are doing this, because sometimes people, even myself, sometimes I do mistakes, you know, not really looking right in the right direction, right? So I look at, you know, v here, okay, not other component. V here is a function, is equal to xz. So when I differentiate it with respect to, x, it is z, okay? So z. dv by dy, the v is not function of y, that means it's going to be 0, okay? Plus w is t y square dv by dz times, so dv by dz is dv by dz, dv by dz, dv by dz, x, yeah, okay, plus dv by dt, oops, dv by dt is 0, because v is not function of, right? So this is your ay vector. Az vector is u dw by dx plus v dw by dy plus w dw by dz, you know, plus dw by dt. Okay, so u is dw by dx, w is not function of x, so it's 0. dw by dy, it is exists, and v is exists, v is xz times dw by dy is sorry if I'm boring, but, you know, I'm just trying to give you an idea about, you know, systematic analysis of these problems. So dw by dy is 2ty, right? So this is all multiplied plus w, which is t. Actually, dw by dz is 0, right? So there's no function of, which means this is 0. Plus dw by dt is y squared, right? So it's y squared. So now it's very simple, right? So how can we find out? Of course, the vector here, the total vector will be this x I plus ay. You can write this equation in the whole form, j plus a z k, right? So you can write the vector if you want like this. Can you get the magnitude of this vector if you want, for example? Can you find out this a? You remember how we do this was, right? It is the square root of, right? Exactly, right? So square root of, if you need to find out, if you have the value of x and y and z, you can find out the values for this. And also you can get the angles, the 3 angles, tan of AY over AX and tan of AZ over AY and so on. You can find out all the angles if you want as well. Okay. Okay, let's get into another definition in this chapter that is talking about something called flow pattern. Flow pattern and streamline and strict lines and stuff like that. You know, you remember these, first, these kind of drawings, like talking about like those lines, right? Those lines are streamlines. It's kind of visualizing the flow. Visualize where, like, the fluid velocity are, like those, colors that you can see here is, if you look at this one here, if I magnify this is velocity magnitude. Okay. So the color here is referring to the red is 25 meter per second. The blue here is 0, or the turquoise here is like 5 meter per second, right? So color can be giving you the velocity magnitude, but also the direction here, and the lines here is to try to visualize the flow. Okay. So that's why we need to, the flow pattern here is something to define or give an idea about, construct what we call it the flow fields. Flow field mean how those flow is, behaving, and right, the domain of the fluids that is changing. So we need to find out these flow fields, how it looks like, what higher velocity, where is higher velocity, where is the lower velocity, and so on and so on. Right? Streamlines has a definition, has a very specific definition, okay, and has a very specific way of looking at those lines. Because of course, when you look at water moving in a pipe, you don't see any lines, right? We are trying to visualize the velocity vectors and so on, right? So it's not a real line. It's just like, it's a solution. It's a way of looking at it. The air around the car, you don't see the air, right? But if you are solving a problem of fluid mechanics around the car, you can draw these lines. So you can find out vortices, for example, turbulence and other things, in order to find out where is the area where it has, higher velocity and higher pressure, low pressure, and so on, right? So streamlines are line drawn from the flow field in a manner that the vector of the velocity at each and every point in the streamline is tangent to streamline. What does it mean? It means that those lines that you are drawing, imagine now you have a tank and the fluid is coming out of this tank here, right? This line that is, you are describing here is basically at any point, the vector of the velocity is tangent to this line. So this is the only definition for the streamline. At every single point, the tangent to these streamlines is, we call it the velocity vector. So the velocity vector. So if you have at every point, you have the velocity direction. So you can plot smooth line that is tangent to all these velocity vectors, okay, which is giving you what we call the streamline. And that's why we know that the tangent of a vector or is a line, the cross product of the velocity vector with the speed, again, this is the path S. So this is the path S. Okay. So at any point here, the vector is, tangent, which means that cross product of a tangent vector and the line vector of S, the angle between these two are 0, which means that the cross product is 0, because it is a magnitude of the first times the magnitude of the second multiplied by sine the angle between these two, and the angle between these two are 0. That means it is 0. So the definition, the mathematical definition of the streamline is when you have a velocity vector and you have a space vector, and the multiplication of these two will be basic, or sorry, the cross product of these two vectors are equal to 0. Okay. There's a lots of application for this, right? So this is actually a cross section of a wing in an aeroplane. So if you look at this here, right? So this is, imagine this is your wing. I'm taking just a cross section here, right? You can look at, you know, the fluids, the streamline around this aerofoil. We call it the aerofoil here, right? So by looking at the velocity distribution, the streamline giving you an idea where those lines are coming together, and, you know, small little, you know, distance between them, because you have higher velocity distribution here than the top one. Of course, like, you know, if you remember from a simple Bernoulli equation, you have higher velocity for the same elevation. Higher velocity mean lower pressure, right? And so on. So you can have an idea about velocity distribution and also pressure distribution. Okay. Stagnation point here is basically a point where, another definition that we have to keep in mind, stagnation point here mean velocity is zero, right? So sometimes streamline is used to find out point where the velocity are zero in, you know, in a flow field. Okay. So again, we are going in general about this topic. I just need you to understand that those are the usage of this kind of type of analysis. There is something called path line and straight line. Those lines are similar to the streamline only when you have an unsteady type of flow. When you have a particle that is moving, and this particle can be with time changing location, right? So now there's something called path line, mean the actual particle position. It's not related to the velocity vector. It is, this particle is here, now it's particle, this particle is here, this particle is here. If you are tracking this, you call this is path line. Okay. Straight line is an experimental definition when you have, for example, you are injecting a smoke in the air to see the line of, you know, of the fluid. So sometimes we test the, you know, car in what we call it the wind tunnel. So we are actually injecting, you know, smoke at one side of the wall from, you know, as the flow is going around the, you know, the car, we kind of visualize, and we actually see it by eye. So we are looking at the smoke, right? The track of the smoke. So the track of the smoke here, it's not really the particle of the fluid. It's just like, you know, the fluid is carrying this smoke, right? So we call it the strict line. Okay. Those three lines are the same, is all the same if you have a steady flow. If you have an unsteady flow, you have different between path line and streamline. Why? Because, you know, the fluid is unsteady. That means even locally changing with time. So the velocity vector here is, you know, or the path of the particle can be different from the tangent velocity at these lines. Okay. And you know, this is what I was talking about here. So people in the design for wind turbines, you're using some of the analysis to visualize the flow around, or in the computational fluid mechanics, when they visualize this in the CFD codes or the computational fluid dynamics tools, they visualize the velocity vectors, and you know, in the form of streamlines. So you can know where is the turbulence and where is, like, you know, the distribution of the higher velocity and lower velocity along you know, the body of the, you know, of the system that you are kind of you know, studying. This is a part, this is basically, so the first part that we'll talk about here is more of a definition and understanding generally how flow field is described, acceleration, velocity, what is a streamline, and so on, right? The first simple analysis for the differential equation is the conservation of mass. Okay, so as I promised you, I'm not going to get into so much detail in this chapter about, like, you know, momentum and energy, because we don't have time for that. Okay, so at least give you an idea about, like, the differential analysis, right? So, and also apply this into one simple conservation law, which is the conservation of mass, the simplest one. Okay, and the simplest conservation of mass, you remember the control volume we are talking about here in the differential form is a very small little control volume. Imagine you are making a small little grid in the fluid and finding out what is coming in and what is going out. Of course, what is coming in and what is going out in the three-dimensional, if you are interested, right? So if you are talking about three-dimensional problem, that means every you know, area of this control volume, the small letter control volume, has a differential change of this mass. So what is the mass? If you remember, mass flow rate is, what is m dot in general? M dot is, remember what is m dot? The function of the velocity. What is the mass flow rate is a function of the velocity. Rho q, okay, or velocity. D, okay. Yeah. No, I'm talking about here, the mass definition is a function of the velocity. Yes, rho q, that's fine. Or rho AV, right? So it's rho A or V times A. If I'm talking about, sorry. If I'm talking about differential mass, that means I'm talking about the density times the velocity of this point times the small little area, right? So, right. Now imagine now I'm talking about this Cartesian, simple Cartesian coordinate system. So I have fluid coming in this area. So what is the area here? The area here is, this is dz, and this is y, so this is dy. Okay, so the area here is dz dy. Okay, if I multiply this area by the density and the velocity in this direction, what is the velocity in this direction? This is x. The velocity in this direction should be the velocity in the direction of x, we call it u, right? This is what the component of the velocity in the x direction, we call it u. So u now, if you multiply this u times rho times the area, which is in this case is dy dz, this will give you the mass coming into the x direction. Okay, now we can do the same thing for y direction. We can do the same thing for z direction. Okay, so there's going to be mass in and there is mass out. The mass out, if you remember, for any differential analysis, you remember we put a certain value, velocity. Yeah, the u is the velocity component, right, in the x direction. Of course, the velocity component in the y direction will be v, right, and the same thing w will be in the z direction. Not the total v, right? It's small component, right? Yes, x component of v. X component of the velocity vector, or the component in the velocity vector in the x direction. So when we say, like, for example, we have a change, we have a mass coming in and mass going out, we can put it in the form of mass in, and there is some mass that is different from the n by some value, right? So that's why we'll see here rho u dy dz plus some change. Some change of what? Some change of the whole thing, right? Some change of d by dx. And of course, this change in the x direction, that means d by dx of rho u dx d, z dy. So I'm taking the same value here, and I take this by d by dx of this whole variable here. So d by dx of this whole variable here is basically this number here. So I have a mass coming in, and this is a mass in, and this is a mass out. Okay. I can take now the, some of you were talking about like the mass in and mass out is equal to the change within the control volume. So I can say this equation here, remember, this is volume times, the density divided by time, which is Q divided by time. I remind you with this chapter 3 main equation, right? So the change within the control volume with respect to the time is equal to what is coming in minus what is going out. Okay. Now I have, for x direction, I have This is out, this is in, okay? So, and I can divide by the volume. What is the volume here? Of the control volume? The volume of this control volume is, anyone? What is the volume of this control volume? Yes, right? dx, dy, dz, right? So the volume of this control volume, dx, dy, dz. So I can put mass in minus mass out, and I also can put, you know, the change of the mass of the system of the control volume, which is rho times the volume of the control volume, and now divide this whole equation by dx, dy, dz. I will end up with this very simple equation. Okay, look at this equation here. It is d rho by dt, d by dx of rho u plus d by dy of rho v plus d by dz of rho w equal to 0, because I put everything in one side of the equation. What this equation is representing the conservation of mass, but now in the differential form. Okay. Later on, and I guess you might guys know what is digitization of the differential equation, maybe in the mass when you are solving the partial differential equation in the mass, where you're changing the derivative by difference, like delta, and right, for a small little volume, right? And this is a way that the computer can read those values. You just need the differential equation in the form of digital value. If the volume become very small, right, you can change all these d by d into a small little differences between 2 points. So if you have numbers, you can just, the computer will calculate those very small little numbers. That's why the idea of presenting the flow field in the differential form. So now the conservation of mass is simply, or this is a continuity equation, d rho by dt plus d rho u by dx plus d rho v by dy plus d rho w by dz is equal 0. Okay, so those are the conservation of mass equation. So this is a general. In differential form. Okay, of course, in the x, y, and z Cartesian coordinates. Okay. Okay, and this is an equation that I want you to remember when you are dealing with fluid mechanics, because this is the most important equation in the differential equation for fluid flow. Conservation of mass is very important to fluid flow analysis. Okay. So now, if I have incompressible fluid, can I reduce this equation slightly? Can I have this equation slightly? What does incompressible mean? Incompressible mean density is constant, right? So in this case, for incompressible, d rho by dt is 0, right? And also rho is constant, right? Which means that I can put this equation now as rho du by dx, because I take the rho from outside inside the integration because it's a constant, plus d plus rho dv by dy plus rho d w by dz equals 0, right? And of course I can divide the whole, because this is 0, I can divide this equation by rho, which means that du by dx plus dv by dy plus dw by dz is equal 0. This is for incompressible fluid. Okay. Remember, we are talking about flow fields, right? So this equation is valid for a flow field. So it has to be satisfied for a flow field. conservation of mass has to be satisfied when we are talking about flow field. So this relation here has to be valid for incompressible fluid. How about for a steady? You know, this is for a steady. Steady flow. If I have a steady flow. No, it's not the same. It's only the change with time is 0. Okay. Did I say compressible or incompressible? I didn't say anything. I just say steady. So steady mean d by dt is 0, which means that d rho u by dx plus d rho v by dy plus d rho w by dz is equal 0. I cannot take rho outside of the derivative because I don't know if, this is only for a steady. So density can be, variable as well. So we have to keep in mind what we mean by incompressible versus what we mean by steady. So this is different. If for a steady and incompressible, steady and incompressible, can I write this same equation here? The first term is 0, and also the rho will be constant. That means du by dx plus dv by dy plus dw by dz is equal 0. Looks like the same as this one here, right? But this one here is valid for incompressible, steady, or unsteady. It just happened that the density is constant. That's why d density by the time is 0, because density is constant, right? But here, density and time are, right? So for incompressible, steady flow, okay? So let's solve this problem so you can understand what we're talking about here. An incompressible velocity field is given by this. So you are given V is unknown, W is B. When we say, okay, velocity cannot change with time. Yeah, again, it's not about the velocity, it's about anything, okay? Steady or unsteady is not related to one parameter, it's related to every parameter. U is ax squared minus y squared. V is unknown, W is B. Where A and B are constant, what must be the form of the velocity component V, B? How can we solve this problem? Yeah, how can we solve this problem? He's giving you velocity component U and W, but V is not known. And he's telling you what V must be, right? First of all, in order for this flow to be a flow field for incompressible velocity field, what has to be satisfied in this case? Yeah, constant density. Okay. Yeah, constant density, sure. Sorry, what has to be satisfied for flow fields? Right? Continuity equation is conservation of mass is valid, right? Now, this conservation of mass is for incompressible fluids. You see here for incompressible fluids is this, right? Right? This is the conservation of mass for incompressible fluids, right? This should be satisfied because this is velocity field, right? So I can say that for in du by dx plus dv by dy plus dw by dz is equal 0, because this is the continuity equation is satisfied. Right? So this equation has to be valid, right? And it's for incompressible fluid. This is a form of the continuity equation or the conservation of mass. So I can just try to plot these together, right? So basically what I need to do, I need to satisfy this equation. So in order to satisfy this equation, du by dx is, what is du by dx? Can you help me with this or keep going? Du by dx is, yeah. My God. Marcos, you lost it, I guess. Y square, it's a square, ax square minus a y square. When you differentiate with respect to x, y square is gone. Thank you. Okay, so in this case we have this term here is, or let me just write it in a different color. This du by dx is 2ax, right? And the other term is 0 plus dv by dy. I don't know what is dv by dy because I don't know even what is v is. Plus dw by dz is dw by dz 0, right? Because w is not function of anything, so it's just a constant. So this is 0. So I can just say that dv by dy is equal to minus 2ax, right? How to find out v in this case? How to find v? Integrate. With respect to y. Excellent. Okay, so in this case I have to integrate with respect to y. So okay, so dv is minus 2ax dy. When I integrate with respect to the y, this is all constant with respect to the y. And right, so it's basically v here is minus 2axy, right? Plus what? Constant. And this constant is it real constant or because this is a partial integration. So the constant should be function of other variable that I'm not integrating with respect to, right? So this should be a function of other variable, which could be, I'm integrating with respect to the y, it could be a function of x and z and also t if I'm, right? Because I don't know what is this function is, okay? In general, yes, c as a x and z and also t because we don't know if, right? Could be a function of t, right? The velocity could be a function of t. Right, so this is your component of the velocity. Of course, if we have more information, we can find out. Of course, a plus c here if you want to, add another constant, right? You can get this information if you have more data provided in the problem. Okay. So similar to this one here, it's this problem here, but it's just like a little bit longer problem. So u is given, okay, and is giving you two-dimensional problem, right? And this is very simple problem. It's not like it just look very strange, but it's just u giving u. We need to find out v. Okay, you need to find the component v, right? So what you need to do is satisfy the continuity equation. You take du by dx plus dv by dy. Now you have dv by dy, you integrate with respect to the y, and then find out the function. So I put the solution for you here. It looks like a lot, but it's just a simple analysis. Okay, I am finished with today's lecture. If you have questions, you can stay around, we can discuss it, but I can stop the recording people can feel comfortable asking.